stuff. So we went a little crazy with hybridization. No, I'm just kidding. We went through hybridization and sort of what it is, and along with obviously our geometries. So a couple important things, right, that we talked about last time. Obviously, you are responsible to know both the electron pair geometry, excuse me, electron pair geometry and the molecular geometry. So remember, again, there's really two names, and one describes sort of the three-dimensional arrangements of all the electron pairs around that central atom. The other obviously describes the overall sort of shape of that molecule. Remember that, really what sort of determines that difference in those names is the presence of those non-bonding electrons or those lone pairs on the central atom. So as we talked about and as we saw last time, if you draw a Lewis structure and pretty much there's no dots on the central atom, then basically the only type of interaction you have going on in terms of electrons are bonding electrons near bonding electrons. And in the terms of sort of repulsionness there, the repulsibility of those two guys, they're pretty acceptable in terms of being near each other. Again, they don't really want to be near each other, but they're okay in that sense. And the other sort of aspect of that is because they're really all bonding pairs that are happening there, you basically got atoms at the other end of all those bonds. And because you have the atoms on the other ends of those bonds, where the electron pairs are and where the bonds are exactly the same. So they sort of lock the molecule into place. And that's why when we look at the names, the electron pair geometry name and the molecular geometry name are going to be the same in that case. It's only when we start introducing really those non-bonding electrons around the central atom that we do get a difference. And as we talked about last time, in terms of the names, the only difference occurs in the molecular geometry or the shape name. The electron pair geometry name will remain the same. So it'll still have 4 electron pairs, 5 electron pairs, however many electron pairs around the central atom. But the difference between sort of, say, 4 electron pairs and 4 bonded pairs is that when we get to, say, 4 electron pairs and only 3 bonds, we have that sort of empty space there. So there is a pair of non-bonding electrons, but there's not an atom at the other end of it to sort of lock this shape of that molecule kind of rigid. So because of that extra sort of space where those non-bonding electrons are, it allows those electrons really to sort of get away a little bit further from each other as they can. And that ends up really changing the molecular geometry name. It also introduces some other types of interactions that we talked about, which are basically non-bonding electrons near bonding electrons. Again, that's getting sort of worse on the scale of electrons not wanting to be near each other. And in certain cases, for example, if we went 4 electron pairs and only 2 bonds, like in the case of water, we now have all 3 of those type of interactions we talked about. We have bonding electrons near bonding electrons. We have non-bonding electrons near bonding electrons. And lastly, we end up with non-bonding electrons near other non-bonding electrons. So lone pairs and lone pairs, or non-bonding electrons each, they are the worst in terms of being near each other. And again, they are able really to sort of go as far as they can from each other because, again, they're both non-bonding electron pairs. They got no atom at the end of it to sort of keep it anchored, if you will. So they're able to really sort of spread out a lot more than when we do have those bonds. The other really important thing that we talked about as well in terms of geometry is when we're doing geometry, and again, only really when we're doing geometry, if you do come across a double bond or a triple bond in your Lewis structure and you're going to apply geometry, we treat the double bond or the triple bond as if they were a single electron pair and also a single bond. They're effectively, even though there's a double bond or triple bond, they're effectively sort of moving, if you will, sort of as one unit, as one effective sort of bonding electrons or electron pairs. So that's really important. And again, we obviously do that just for geometry purposes. And if you were asked just a straight question of how many electron pairs there are and not related to geometry, you obviously would count them like normal. But in terms of geometry, we do that. We also saw a lot more geometries that maybe you have not seen before, and a lot of those basically revolve around those expanded octets that we talked about. Again, sulfur on the periodic table going left, going right, and going down in the nonmetal region where sulfur is typically those guys, again, available to really go above 8 and do that expanded octet. That expanded octet is really made possible by the fact that they are on basically the third energy level or greater. And what happens at third energy level or greater is that's when we first start to see those d orbitals available to them. And that allows them the opportunity really to sort of do the expanded octet. And as we talked about last time as well, the ones before that, like carbon, nitrogen, oxygen, which is in period number 2 or n equals 2, they don't have those d orbitals available to them. So you should never, make carbon go above 8 because it really doesn't have the ability to do so. Any questions on that stuff we talked about there? Now, we also then continued into the lab and we started talking about hybridization. And the idea of hybridization is, sort of a model of bonding that allows us to explain certain sort of bond angles that we see in certain molecules. And the idea there is we mix some atomic orbitals. And remember, atomic orbitals are really like our s orbitals or p orbitals or d orbitals and so forth. All those guys, as you know, hopefully have different shapes. They also have different sort of energy levels at which they are at. And the idea behind sort of hybridization is we take those guys, we sort of mix them together. And what we end up with are what I refer to as hybrid orbitals, which essentially end up, in theory, with the same sort of shape. So again, it's sort of like the idea of we're going to put like two circles together, probably going to come together a lot better than what's that one trying to put like a circle and a square peg or something like that, right? It does not going to probably fit so well. Things are different shapes. And, if we just try to slap together perhaps an s orbital and like a p orbital, again, one's sort of a circle, if you want to think about that, or a spear. One's like a figure 8. And again, there are sort of different energy levels. And that makes for perhaps not the best way for those orbitals to sort of overlap with each other. So the idea of that, we kind of mix these atomic orbitals, which are in different energy levels. We actually reduce the energy down, which is also always a good thing to kind of bring things to a lower energy. And we end up with these hybrid orbitals that are similar in shape, similar in energy, and makes for sort of better overlap. How do we figure out sort of the hybridization of something? Again, as we talked about, you want to really keep it simple. So I drew this little thing here to the right a number of times, I think the other day. And this is really a good way to sort of approach hybridization. Really, hybridization is really all about electron pair geometry. So when we talk about that electron pair geometry, that is really where our hybridization really is sort of based upon. And, if you had, say, 2 electron pairs, that is linear in terms of its geometry. And again, if you write this S, P, and D sort of situation here, pretty much you could just count. So 1 and 2 always starting at S. That's basically one s orbital and one p orbital gives us an sp hybridization. 3 electron pairs in terms of its electron pair geometry is our trigonal planar. And 3 electron pairs, again, just counting 1, 2, and 3. That's an S and 2 Ps, which gives us sp2. 4 electron pairs around whatever you're counting there is a tetrahedral geometry for our electron pairs. Again, 1, 2, 3, and 4 here. And that would give us sp3 hybridization. 5 electron pairs going into our sort of expanded octet like this slide shows. That's going to be your triangular bipyramidal. And again, you can do the same thing. 1, 2, 3, 4, and up here to 5. and that gives us an S, 3 Ps, and now we're into our Ds. And lastly, 6, which is octahedral. Again, counting 1, 2, 3, 4, 5, and 6 here. And that is basically an S, 3 Ps, and 2 Ds. That is really by far sort of the simplest way to figure out the hybridization. You do want to remember, though, you want to really count electron pairs around whatever atom you're applying hybridization to. A lot of times it is a central atom. It could be an outside atom if it's not hydrogen. Hydrogen will not go through hybridization because it basically only has one electron. And if you remember, as we sort of saw with those arrows and stuff, part of the hybridization process is an electron gets promoted upwards. So obviously if it only has sort of one electron, it can't do that. And then, we'll have some empty orbitals. So hydrogen doesn't hybridize, but, probably anything else that you have there, especially like central atoms, oxygen's on the outside, you can probably apply hybridization to. We do count, though, the electron pairs the same way that we do when we do geometry, which means if it is a double bond or a triple bond, it again will only count as one electron pair. So, that is sort of the way you want to do hybridization. So again, if we had something, like, this guy here, if we look at the central atom, which is sulfur, and we wanted to apply hybridization, we would count 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. 4 electron pairs would give me sp3 hybridization. And that is the best way to do it. And again, if you were starting at scratch, you would start here and go 1, 2, 3, and 4. And that would give me obviously sp3. So that's the really approach you should take with hybridization. As I mentioned the other day, I'm not going to ask you to draw sort of the arrows and where all the electrons end up and stuff like that. It ideally was there to kind of help you maybe visualize sort of where things are going, where things are ending up. But you really just need to be able to, if you draw your Lewis structure, be able to apply that hybridization. Any questions on hybridization that we talked about? Now, in addition, we start at the end there, really started, or also talked about, was referred to as a sigma bond and a pi bond. And based on sort of the hybridization of a particular sort of central atom or a couple of atoms, we'll end up getting sort of a sigma bond formed or maybe some pi bonds. And again, this as well, you probably want to keep sort of simple in that sense. Just kind of do it's kind of straightforward. And what I mean by that is, ultimately you could think about it like this. If we have a single bond, such as this, or if you want to think about it like the first line that you draw to make a bond, if you're drawing a Lewis structure, that's probably going to be a sigma bond. And really what that means is, we have these orbitals and they're just going to come like straight at each other, what is sometimes referred to as head-on sort of overlap there. And that makes that sigma bond. When we have a double bond, it is also made up, and again, you can kind of just keep it simple. If you're going to draw a double bond, you would draw one line first, probably a lot better than that crappy line I just drew there, but we'll go with that. And that's going to be a sigma bond there. We would then draw a second bond to make a very bad looking double bond there. And that second line, if you want to think about it, is basically going to be a pi bond. And where does the pi bond come from? As we talked about, through the hybridization process. So for example, if you just look at something like sp2, and if sp2 basically means that I took an s and 2 of these p's, right? What that means is there's one p orbital that doesn't get hybridized. It remains a regular run-of-the-mill p orbital. And with an sp2 hybridization, you will actually have a pz orbital that is unhybridized. It also still will have one electron in it. And again, it will just look like a regular sort of run-of-the-mill p orbital. And if you had a double bond, whatever that guy was double bonding with might also have a similar unhybridized p orbital there. And it also would be just like a regular p orbital. And the difference, sort of how these orbitals sort of interact with each other, is different than, say, in a sigma bond. Because when you look at like a p orbital like this, the probability of where you would find perhaps an electron is it's kind of in these loopy areas, if you will. This is sort of the highest probability of where probably those electrons are housed. And what happens when these two p orbitals come together is they want to kind of come together in those areas where we would expect, some of those electrons to probably be. And that will allow for really those two orbitals to sort of adequately and pretty efficiently share that electron. And this type of overlap, it was sometimes referred to as side by side or sideways overlap. And it's above and below sort of the plane of where the bond is happening. And it's really because of, that's sort of where you would expect to find, those electrons to be housed. If they decided to do more of like a head to head sort of overlap, you would have essentially these p orbitals sort of very badly drawn there. Let's try that again here. Come here. It's the end of the week. The drawings aren't the greatest. I know they're not the greatest at the beginning of the week either, but I like to think so. So we would get something like this, maybe like a figure eight sort of happening. And what would happen is, we would get this sort of area into two orbitals that maybe we could find an electron. But what happens, say the electron's over here and over here, there's really no interaction happening between that side of those p orbitals. And that's why they don't really come sort of head on at each other. It doesn't provide for very efficient bonding. So that's why we get this more side to side overlap that's happening with our p orbitals. And that ultimately is sort of where that second line or the double bond or pi bond sort of comes from. Now, in a triple bond situation, we have sort of the same thing. Again, kind of like the first line you would draw would be your sigma bond. Second line would be like a pi bond. And the third line would also be a pi bond in that case. So a single bond is typically made up of just a sigma bond. A double bond is made up basically of two types of bonds. One is the sigma bond and one is the pi bond. And a triple bond is made up of, I think I'm back. I felt like I froze there. A triple bond is made up of a sigma bond and two pi bonds. And that's because ultimately what's going to happen is when you get to sort of a triple bond situation, you're going to probably be in an sp hybridization. And what that means, if you're in an sp hybridization, you essentially are just doing this guy and this guy. That's going to allow not one, but two run-of-the-mill unhybridized p orbitals to be available for this sort of side-to-side bonding. And you will get basically two pairs of p orbitals doing this side-to-side bonding, and each pair would represent one of the pi bonds that you see in a triple bond. So the simplest way to sort of look at something like that is, try to figure out where I'm at. There it is. You would just simply just kind of look at something and, count what's going on there. So if we were looking at this particular guy here, that is a sigma bond, that's a sigma bond, that's a sigma bond, that's a sigma bond, that's a sigma bond, and there would be in this double bond one more sigma bond. So that's like 4, 5, and 6 total in this deal. And obviously the other line in the double bond would be the pi bond that would occur. So that's sort of the simple way to identify those things. Any questions on that stuff there. All right, so we're going to sort of finish up the bonding talk here. We're going to talk now about really what is known as molecular polarity. And molecular polarity is talking about the entire molecule basically as a whole. So if you remember earlier on, we sort of talked about the sort of bond polarity. And when we talk about bond polarity, you know, we're really talking about that difference in electronegativity value. So if you remember, right, it goes from like 0 to 4. And again, if we take that difference in electronegativity values and we had 0 to like 0.4, that's considered a nonpolar bond, or the electrons are going to be shared pretty equally. If we did like a little bit above there, like maybe 0.5 to less than 2, that's going to be some type of polar bond where we're not going to share the electrons equally. And if we're typically above 2, you know, we're not going to get any sharing of electrons. We're most likely going to get more ionic bonds. Now, when we talk about molecular polarity, what that means is we're talking about the entire molecule as a whole. And it does sort of depend on the type of molecule you're dealing with as to, you know, sort of what you should look at in terms of, you know, is this molecule as a whole going to be polar or nonpolar? If something is polar, it will have what is referred to as a dipole moment. And a dipole moment is actually displayed kind of the same way as we use those bond dipole arrows. But what this means is you'll typically have a sort of bigger arrow if you want to draw it that way, or a sort of dipole moment arrow. And what it still means the same, where it points to is more negative in the molecule in this case, and where it sort of makes a plus sign on the back end would be more positive in terms of the actual molecule as a whole. If something is a nonpolar molecule, what that means is the entire molecule as a whole is pretty much sharing electrons pretty equally. And that means that we would expect the molecule to, I don't want to say be neutral, but really have no sort of difference in charge. As opposed to something that is polar, what that means is in the entire molecule, because of the unequal sharing of electrons that are happening, there's a side to that molecule that's more negative, and there's a side to that molecule that's more positive. Just like we did with our electronegativity values there, you know, if it's a polar bond, there's a side to the individual bond that is more negative, and there's a side that's more positive in that individual bond. So let's start with really the sort of simplest ones to determine, you know, molecular polarity. And these are really diatomic molecules. And diatomic molecules are probably the easiest to determine because simply there's only two things there, basically. And because there's only two atoms present, what that usually means is there's really only one bond there as well. And because there's only one bond, if you could determine that that bond is polar, what that would mean is that the entire molecule would also be polar. And if you were able to determine that that one bond is nonpolar, you would be able to determine that that molecule is going to be nonpolar. And the reason for that is because there's only one bond. So because there's one bond, if that one bond is polar, the actual molecule will be polar, and nonpolar, it obviously will be nonpolar as well. So if we have a homonuclear diatomic molecule, that is a big word that says basically two of the same. So if you have two of the same elements like H2, F2, doesn't matter if it's single bonded, doesn't matter if it's double bonded like O2. I'm not sure why 1O is bigger, just imagine it's not. Doesn't matter if it's triple bonded. all these guys, if you did the difference in electronegativity values, would give you a difference of 0. And because of that, each of them have a nonpolar bond. That bond right there, that double bond right there, that triple bond right there. Now, because that again is the only bond we see, this guy has a nonpolar bond. And what that would mean is that the molecule is also a nonpolar molecule because of that. And again, it really is that simple in the case of diatomic molecules because that is the only bond we see. If that happens to be nonpolar like it is in this case, then we would expect the entire molecule obviously to be sharing those electrons equally. Question on that there. Now, when you get to something which is heteronuclear, kind of like a heterogeneous mixture, that means that you have more than one element present. They typically will have a dipole moment. So if we took something like HF, again, if we did some difference in electronegativity values off the top of our head, gives us a 1.9. That 1.9 tells us it is polar heading towards the fluorine. Again, this is a polar bond. And because that's the only bond, it would also be a polar molecule because of that. And that arrow would represent both the bond dipole, but it would also represent the dipole moment in this guy. So this arrow here would be its dipole moment. And again, basically what that means is if we were looking at HF as a whole, the fluorine side would be more negative. The hydrogen side would be more positive in that case. Same thing if we laid up something like HCl. Again, if we did some differences in electronegativity, I won't go off the top of my head what it is, but we will get a polar bond where chlorine is more polar or more electronegative than hydrogen. And we would get this one bond being polar bond, and same reason as below, because that's the only bond, the molecule would be polar as well. So this would be a polar molecule, which means this arrow would represent both the bond dipole here and also the dipole moment. And again, what that means is the chlorine in this case is more negative. The hydrogen is more positive. So really the sort of nice thing about sort of diatomic molecules is they're relatively simple in the sense of figuring out, is something going to be polar or non-polar? And they're really simple because of that fact. They have pretty much only one bond. So you could use, actually, this is the case where you could actually use the difference in electronegativity values to figure out the bond polarity, and it will also tell you the molecular polarity as well. Question on diatomic molecules. So if everything was that simple, that would be awesome, but it is not. So it does get a little bit more complicated when we start dealing with things that have 3 or more atoms involved. So when you have things that have 3 or more atoms involved, we do have to look at a couple of different things. And first off, let's talk about sort of the 2 things that you really have to look at. If you got 3 or more atoms, and you want to know, is this thing going to be polar? First off, you need to check, are there polar bonds? So if there are no polar bonds, then you can probably stop right there. The molecule is going to be nonpolar to begin with. If there are polar bonds, you might think, well, I could probably stop there as well because there's polar bonds. It would make sense that the thing is polar. And the answer would be not necessarily. So if you do have polar bonds, the other really important thing that you need to look at is the molecular geometry. And when we think about sort of polarity, sometimes people think about it this way, and sometimes it's a good way to sort of think about it, is sort of think about it like a tug of war, right? So, if you have two things kind of pulling on a rope in a tug of war, the little flag in the middle is going to kind of stay there, right? If they're pulling equally. But if you get somebody on one side that could pull a lot harder than somebody on the other side, that little flag is going to start moving, right? And then eventually everybody falls into the mud pit. Everybody has a good laugh. It's a good time. But in this case, what we're looking at in terms of that pull is actually the like electronegativity, and how they are pulling on each other has a lot to do with really their three-dimensional arrangement to each other, basically their geometry, how they are, where they are located. If people pull equal and opposite of each other, they're going to kind of not do anything. If people kind of pull unequal to each other, you're going to see a lot of movement sort of happening. So let's take a look at a very common example of molecular polarity and try to work through, how we sort of get to the answer that we do get to here. Let's take a look at our good friend carbon dioxide. So we draw a nice Lewis structure here of carbon dioxide. Looks something like that. Now, when we look at the individual bonds in carbon dioxide, we have carbon and oxygen. And again, really, you don't need you don't really need those electronegativity values for something like this. This is sort of the arrangement of carbon, nitrogen, oxygen, and fluorine on the periodic table. They're all in the same period. And what we see is oxygen is further to the right in the same period. That would mean that it is more electronegative. And we would anticipate that there is a polar bond heading towards the oxygen, like that. And there would also be another polar bond heading towards that oxygen. So something like carbon dioxide does have polar bonds. So again, in this situation, you may say to yourself, well, I'm going to go out on a limb here and go, I think it is a polar molecule. But we do have to look at the second thing, which is really important, and that is the molecular geometry here. So if we went to the carbon atom here, on the left-hand side, we have one electron pair for the double bond. On the right-hand side, we have one electron pair for the double bond. That is two electron pairs. We also have one bond on the left, which is the double bond, one bond on the right, and that is two bonds. So the molecular geometry here is something that is linear. So why would sort of the molecular geometry or the shape of this molecule really, affect the polarity of it? Well, you could just do sort of a simple example. Basically, you have carbon dioxide in a straight line, and you got an oxygen on this side pulling, and you got the oxygen on the other side pulling. And literally, I am pulling on my pen here, and you can see my pen is hopefully not going anywhere. And it's really not going anywhere, because what we have here is somebody on the left-hand side, and again, back to sort of the tug of war on the rope sort of example, we have somebody pulling to the left just as hard as somebody is pulling to the right. So what ends up happening is they cancel each other out. So although this guy has polar bonds, because of the geometry here, they actually will cancel one another out. And what that means is this guy would actually be a nonpolar molecule. So carbon dioxide is a very good example of something that could definitely have polar bonds, but because of the molecular geometry, will cancel each other out. Why do they cancel each other out? Well, those little lines, those dipole arrows that we draw on top, those are really what we like to call vectors. And I believe they have direction and magnitude. And then I fell asleep in physics, but I woke up long enough to remember that in certain cases, they will sort of cancel each other out. And in certain cases, they will sort of add to each other. So that is why the sort of molecular geometry here is really important. And again, if you want to keep it simple, think about it like pulling on a rope. And again, people on opposite sides pulling on a rope, like we have here, are going to basically sort of cancel each other out. Same thing, by the way, if they're sort of heading at each other. And you could kind of think about it like two people on opposite sides of a swinging door. If they're both pushing equally, the door is really not going to open, right? So that's, again, another way that you could kind of get, something to cancel out in terms of those bond polarities or bond dipoles. Question on that? Okay. Then let's take a look at another sort of common example, and that is our good friend here. That is our good friend water. And when we look at water, looks something like this. And again, here, the first thing that we really want to look at is, are there polar bonds in water? And when we talk about are there polar bonds in water, what we are looking at is the electronegativity difference in this case between the hydrogen and the oxygen. And again, between the hydrogen and the oxygen is going to be more electronegative. So we could draw bond dipoles heading in this direction towards the oxygen. And we can also say, like we did above, that this guy does have polar bonds. So what does that mean? Well, again, here we do need to look at our geometry. And the geometry of this guy is, if we look at the oxygen, there are a grand total of 4 electron pairs. There are only 2 bonds. So as we talked about the other day, this is a geometry known as bent or V-shaped, which is why I drew it like that. So what does that mean? Well, if you kind of think about what's happening here, you got a geometry sort of like this. You got one guy coming this way, you got one guy coming this way. They're going to kind of meet up here on top. If you have something like this, if you think you kind of get in the center there and just pull, you would kind of imagine the whole thing sort of moving. And what we end up getting is actually a net dipole moment that occurs in this case, heading towards the oxygen. We get a net dipole moment that basically occurs in this direction. And that, again, is our dipole moment, where the oxygen side of water is more negative, the hydrogen side of water is more positive. And again, just so you know how we kind of get there, you take this little bond dipole or vector, kind of do that move. You take this guy, which is heading this way, kind of go, head to tail there. And then basically we get our net dipole moment when we sort of add those guys together, heading upwards in sort of this direction here. I'll just kind of draw a little higher there so you can see it. But that's where we kind of get our dipole moment that basically occurs in this case. So water would be polar. It does have polar bonds. And because of water's geometry, it allows it to basically be polar in this case. And that's different than CO2, which, also does have, as we saw, polar bonds. But because of its geometry, it doesn't allow it to really affect it. So they sort of cancel each other out in that case. Question on that there. Now, who wants to draw these vectors? Who wants to, think too much about this? We want to maybe think about a way that we can maybe figure out a simpler approach to figuring out sort of polarity or molecular polarity. where, you know, you'll be okay most of the time. So let's talk about sort of a way we could do that. And let's just try somewhere to scribble. I'll scribble over here, I think. Well, when we look at certain geometries, and I'm going to do is kind of erase this, so I got some little extra room here, I think. When we look at molecular geometries, there are certain geometries which are referred to as being sort of symmetrical, and there are some which are sometimes referred to as being unsymmetrical sort of geometries. And what does that mean? Well, symmetrical geometries are some geometries like this. So if you have what are sometimes referred to as symmetrical geometries, and what we're talking about here again are really molecular geometry, our shape. These are things like trigonal planar. These are things like tetrahedral. These are things like triangular, bipyramidal. These are things like octahedral. And again, if you draw a Lewis structure, if you sort of identify, I guess not sort of, but if you identify it as one of these molecular geometries here, what do they all kind of have in common? Well, if you remember, if you look at the Lewis structure, there are no non-bonding electrons around the central atom. So basically, when you draw your Lewis structure, that's a really bad dot there. There are basically no dots. I guess I should actually put no next to that. That would probably be good. So when we draw that central atom, we have no dots. I'll just write it that way. No dots around the central atom. And the other thing is, if you have that situation where you draw a Lewis structure, none of those non-bonding electrons around the central atom, and the other thing is every atom on the outside is the same element, it will most likely in every case be a nonpolar molecule. And why is that? Well, it's because they are symmetrical, which means everybody, all the atoms that are there, they're pretty much equal and opposite of each other in three-dimensional space, which means if we have the same atoms on the outside and they're equal and opposite of each other, they're essentially going to pull equal and cancel each other out. So kind of like two people, again, pulling opposite sides of a rope, they're going to pull equally, and all the dipoles will basically cancel out. So for example, if we looked at this particular guy here, do this guy, we'll do this guy. And we'll do one more guy here. Now, between carbon and fluorine, definitely fluorine is going to be more electronegative. And we would expect, again, if we drew those sort of dipole arrows, they're going to basically pull equal and opposite of each other. Again, we don't see any dots on the central atom. Everybody on the outside is the same. This would be a nonpolar molecule because basically, even though, again, it has polar bonds, and this is really not drawn three-dimensional, right? And I will give it a try, and I'll probably butcher it here. But remember that tetrahedral sort of arrangement is kind of like this. And if you have that fluorine here, they're sort of in three-dimensional space, sort of pulling equal and opposite of each other, and they will basically cancel each other out. So this is a case where you really don't even have to draw these kind of individual bond dipoles unless you're asked to do so. You literally could come over here and go, I see the central atom. I see everything on the outside is the same. And my central atom doesn't have dots. I'm going to go with nonpolar in this case. And you would be right. So that's a very sort of easy way to determine perhaps if something is nonpolar. Some type of symmetrical geometry, no dots on the central atom, everybody on the outside is the same, and you'll end up with a nonpolar molecule. But what happens though if we took one of those fluorines and we swapped it out for hydrogen, for example? Well, we still got our polar bonds heading towards fluorine. But now on the sort of right-hand side here, we have a carbon-hydrogen bond. Carbon-hydrogen bond is a nonpolar bond. And even though it's nonpolar, there's going to be no sort of separation of charge. But in reality, carbon is a little bit more electronegative. So what you got is all three of these guys sort of pulling this way. And hydrogen is really not pulling that way at all. In fact, he might even be kind of helping a little bit, pulling in the same direction. So you could kind of imagine if everybody's sort of pulling in one direction, there would be sort of a movement that would occur. And because of that atom not being the same on this side, we will actually become a polar molecule because of that. So it's like these three strong fluorines are definitely pulling in this direction. There's nobody sort of pulling it back in the opposite direction. And again, sort of, it's like three people went on one side of the rope and started pulling, and one poor guy was on the other side trying to hang on. Might be able to hang on for a bit, but probably going to get pulled away. And that's sort of what we have going here. So a very nice sort of way you could kind of quickly identify molecular polarity in terms of nonpolar or polar when you're dealing with these symmetrical geometries, these molecular geometries, is simply if you draw your Lewis structure, if you look at your central atom and you see no dots, you see everything on the outside is the same element, just write nonpolar molecule, you'll probably be right. And that's what happened there on the left. If you do your Lewis structure and you see no dots on the central atom and everything on the outside is not the same element, it's probably a safe bet to write polar molecule. And that's what happened there on the right. Question on symmetrical geometries here. So with symmetrical geometries, that would make sense that there might be something that is referred to sometimes as unsymmetrical geometries. And maybe I'll do it here. So I've got somewhere to scribble. Remember if I had anything going past that. Get this out of the way. All right. So let's talk about some unsymmetrical geometries here. Well, some unsymmetrical geometries. And again, we're talking about molecular geometries. Are that shape. These are things like perhaps trigonal pyramid, angular, bent or V-shaped, square pyramid, little seesaw. What all these guys sort of share in common is, if you remember when we looked at these geometries, there are non-bonding electrons on the central atom. So that means when you draw your Lewis structure, you will see dots on the central atom. And kind of like our other guy, if you draw a Lewis structure and you have dots on the central atom and all of the outside atoms are the same, you're probably going to end up with a polar molecule, kind of a pretty safe bet on that. Example of that is our guy we just did. That is water. I drew Lewis structure. I see dots. I see same. I see polar molecule. So that is definitely one super easy way to sort of figure out the polarity of something that is unsymmetrical. And that is what you're looking for. You are looking for dots on the central atom. You're looking for the same elements on the outside, and it will most likely be polar. If you don't have the same elements on the outside, you should kind of look at, what those elements are and the electronegativity differences. But probably most of the time it will still be polar, but you should definitely kind of look at it to see there's no weird sort of situation happening. But most of the time it should definitely be polar. So that is our unsymmetrical geometries. So what does that leave us? It kind of leaves us really, one important guy, which is the molecular geometry of linear. And because linear is essentially a straight line, that one you sort of has to think about as to, are you going to get a polar bond or not, or polar molecule or a nonpolar molecule? But the nice thing about it is it's pretty much a straight line, which means, if you got something like this and all the dipoles go in opposite directions, they're going to cancel. And it's going to be nonpolar molecule. And again, that's sort of equivalent to me pulling on both sides of my pen. You could also have one where they maybe head in the same direction. They will also sort of cancel each other out, and you'll end up with a nonpolar molecule as well. Again, sort of equivalent to two people pushing on the door on opposite sides. Equally, the door won't really swing open. But you could potentially have a straight line situation where everybody is going kind of in the same direction, and that would be obviously a polar molecule. So linear is one where you do have to sort of think about, whether or not it's going to be basically polar or non-polar. But again, because it's a straight line, it makes it relatively easier to sort of do that. Any questions on that there? Now, there actually is a couple of geometries that we didn't talk about here, but there is kind of a couple of geometries that are maybe some exceptions, and they really don't fall with our unsymmetrical geometries. They actually fall with our, wherever I went with that, so the other way, I think. They fall with our more symmetrical geometries here. And those guys are actually some of our expanded octets. So we have a couple of expanded octets that will actually sort of fall into this category as well as being, sort of considered, symmetrical geometries, even though they have sort of dots on their central atom. So if we look at something like, linear, and the linear I'm talking about is the expanded linear. And if you remember, that is our guy kind of like this. Maybe a little dot, 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 dot type situation. And what ends up happening here is all those non-bonding electrons, they kind of make a nice little triangle type thing. They sort of cancel any effect that they may have on each other. But we do have, the X and the X, which is linear from each other. And again, if they're the same, we're going to get that same sort of opposites here are going to cancel each other out. So this linear where we have dots, I'll put it that way, the expanded octet, is actually one where you could potentially have something with dots around the central atom, but because it's linear, it's basically back to a straight line situation. So if they're the same atoms on the outside, they will actually cancel each other out, even though they happen to have some dots happening there. So that's one sort of exception that you might go, hey, it has dots. How come it's going to be nonpolar? And again, this would be nonpolar in this case. And it's because it ends up being relatively symmetrical in that sort of situation. The other one that, ends up being pretty symmetrical as well, that also has dots, is another expanded octet, and that is our square planar. So if we remember what our square planar sort of looks like, draw that guy up real quick. Our square planar is, basically we have this central atom here. We got some dots happening. And then we kind of have at the corners here some bonds, right? And those guys make essentially a nice square that happens, right? So if you remember, that makes it square, which is why it's known as square planar. Makes basically a square within a plane, which means if all these guys on the outside are the same, they're basically going to be pulling opposites of each other, so they would cancel. They would be pulling opposites of each other, so they would cancel as well. And again, even though there technically are some dots happening here, this also would end up being a nonpolar molecule because of that. Question on sort of a quicker approach to figuring out molecular polarity. And obviously this is involving things that there are 3 or more atoms involved. Any questions on that there? Let me see here. Let's take a look at so let's take a look at maybe some examples here, and let's give you an opportunity to try to determine if it's polar or non-polar molecule. Let's kind of jam through these real quick. So I have somewhere. I think I might. We'll come back here. Did I put some extra places to write? Yeah. Okay, perfect. So why don't you take a look at a few of these here and decide if they are, and we're going to come back to everything I just skipped by. I just want to get to somewhere I have somewhere to write. Take a look at each of these molecules here and try to decide, is this molecule going to be polar or non-polar? Again, the molecular polarity is what we are talking about here. Let's do... No. Guess I should probably plug it in before the lecture's over quick, huh? Oops. Oh, give it the old save. All right. Let's see. I know. That would have probably been good, huh? Let's do that there. And let's see what else we got there. Let's do this guy here. Let's do... did that, we did that. Let's do this guy. Let's see, that. Yeah, why don't we do this? All right, so take a few minutes here and decide for each of these, are they going to be a polar molecule or a non-polar molecule, and see what you come up with here. Okay, let's take a look and see how we're doing. And again, we'll just kind of take the maybe quick approach here and sort of the ways you should kind of look at these guys. All right, so first off here, I'm going to look at my central atom here. I see no dots, which maybe makes me think it's symmetrical. But I do want to look at the geometry here. And if I look at the central atom, it's got 2 electron pairs and it's got 2 bonds, which means this geometry here is actually going to be linear, right? So this geometry here is linear. So it's a straight line. So we want to think about what we got going on here. We have the carbon-hydrogen bond on the left. That is a nonpolar bond, right? So difference in electronegativity there is 0.4. The carbon-nitrogen bond, carbon and nitrogen are in the same period. Nitrogen is further to the right, which would tell us that nitrogen is probably more electronegative, which means we could draw that arrow there. So we got basically a straight line where the only person pulling is the nitrogen. And again, you could kind of imagine tug of war. If he was pulling to the right, the whole thing would move. This guy would be a polar molecule because of that. That arrow there would also represent the dipole moment that's happening there, which means the nitrogen side here would be more negative. The carbon side here would be more positive. Question on that one there. All right, so taking a look here at my next one, I got no dots on the central atom. I got me everybody the same. And I know this is tetrahedral in terms of the geometry. So no dots, everybody on the outside is the same, going to be nonpolar molecule. Now, let's be very clear. The molecule is nonpolar, but is there a polar bond in here? And there probably is between the carbon and the chlorine, probably going to be polar bonds. But again, because of the symmetry of that tetrahedral shape, they're going to cancel each other out. So it would be a nonpolar molecule in this particular case. Coming over here to my guy on the right, I got a central atom, no dots, so maybe symmetrical. When I look on the outside, though, they are not all the same, which means this guy, by the way, is trigonal planar in terms of the geometry. But this would become a polar molecule because of that. The carbon-hydrogen bonds are nonpolar, but the bond between carbon and oxygen there is polar, and our dipole moment would be happening heading towards dipole moment over here, heading towards our oxygen in this case. Meaning, again, here, the oxygen side of this molecule more negative, hydrogen's carbon side really more positive. Question on that one there. So again, although it is symmetrical in terms of its geometry, because we have a different element involved, we're going to get, again, sort of if 3 people were pulling on this string and one person pulled a lot harder than the other 2, they would probably start moving the rope towards them, and that's where we sort of end up happening. Coming down here to NF3, I got a central atom. I see dots. I see everybody on the outside is the same. I see polar molecule. And again here, what's going to happen is this is trigonal in terms of the geometry pyramid, which is one of our unsymmetrical sort of geometries here. This is CO2 in the middle. If we just look at geometry, not necessarily the charge that's there, this guy in the central atom has no dots. Everybody on the outside is the same, and this would be trigonal planar here. So no dots, everyone on the outside same, going to end up canceling each other out. Going to be nonpolar based on its geometry. Any questions on that one there? Coming over here to SO2, I see central atom, I see dots, I see outside ones the same, I see polar molecule. And again, between sulfur and oxygen is going to be more electronegative. So, we got this guy going this way, this guy going this way. And again, drawn in sort of 2-dimension, and may look like they're going to cancel each other out. But remember that the geometry here is angular, which means they're really looking more like this sort of situation in terms of its geometry. Oops. Which means, again, we're pulling down that way, we're pulling down that way. They're not directly going in opposite directions. They are going to basically add to each other, kind of vectorness, if you will, in this kind of net direction coming this way. Yes, heading down. Any questions on that one there?
I just had a quick question. So it's angular because it's a polar molecule?
No, it's angular because of the electron pairs and the bonds that are present. And because it's just like we were doing geometry earlier, there's 3 electron pairs, but only 2 bonds. And because of that kind of non-bonding electrons, what ends up happening is there's no bond up on top. So those bonded guys start moving this way, and the non-bonding guys are moving the other way. And what it does to the overall shape of it is it actually kind of angles it at about just less than 120 degrees, not like the bent or V shape like in water, which is 100, less than 109, but a little bit less than that. But because of the geometry, actually, it's actually because of the geometry that it actually is a polar molecule. So it's actually the opposite of what you asked. It's really the geometry and the polar bonds that make it a polar molecule.
Okay, thank you.
You're welcome. Other questions? Okay. So let's see. We got that. Where we got? We'll come over here again. We look at the central atom. We see no dots. I won't draw the 6 arrows, but we see everything the same on the outside. And again, that's going to lead us to a symmetrical geometries. This is obviously octahedral in terms of the geometry, and it would be a nonpolar molecule. Again, in 2-dimension, not really drawn perfectly in terms of where they're all located, but almost. You kind of think like these guys are sort of opposite of each other. These guys are opposite of each other, and then obviously the up and down would be opposite of each other in sort of 3-dimensional space. So because they're all fluorines, they're all going to kind of be pulling equally to each other and canceling out. So that leaves us one last one here, I think. Dead center here, we got a carbon, no dots. So we may be tempted to go with a nonpolar molecule, but we do want to look and we see hydrogens, but we do also see chlorines. So here we do not have all the same atoms on the outside, or elements on the outside. And when we have that situation with no dots and not all of the same elements on the outside, it's going to most likely be a polar molecule. And that's because of this polar bond here, this polar bond here. In reality, the dipole moment is probably heading somewhere in that direction towards the chlorine. Hopefully you could kind of see a pattern. It's probably the best way to sort of do molecular geometry is to sort of do that symmetrical, unsymmetrical, dots, no dots type of situation. Because to be honest with you, most people, including myself, have a very hard time 3-dimensionally visualizing things. So by just drawing your Lewis structure, you don't even necessarily have to draw it with geometry involved or anything like that. But as long as you can identify the geometry, and literally you don't even necessarily have to identify the geometry, as long as you can identify the dots on that central atom and all the elements are either the same or not the same on the outside, you probably in 97% of the time will get the right answer when you're asked, is it a polar molecule or a non-polar molecule? Questions on that? let's just go back over some of these ones that we skipped. Just, it's kind of like what we just did, but just to see them here. Okay, I think that's where we stepped in. So this is an example of HCl like we talked about. And again, those are really sort of the easiest ones because they're diatomic. And because that is a polar bond, we would expect the entire molecule to be polar. And what that means is this is kind of like the electron cloud. So we would expect to find more electrons kind of hanging out over here, going to make this side of the molecule more negative and this side more positive. There's our CO2, as we talked about. Again, because of the geometry here, which is linear, even though these guys have polar bonds, that geometry is going to allow it to basically cancel out. And what do we see is, kind of this pretty equal distribution of electron cloud over the entire molecule, which essentially means that there is no spot that's more positive. There's no spot that's more negative in this case. You would expect you could kind of think of it as being neutral. It doesn't have a positive side or a negative side. Kind of has no charge associated with it. There's our water, as we talked about. Again, because of the geometry here, it's going to allow those bond dipoles to add to each other, and that's going to give us a net dipole moment happening right through the center of the molecule, where again, the oxygen side is going to be more negative, hydrogen side going to be more positive. And we kind of see that here. The kind of red color is sort of, if you kind of make that out maybe on your side, the red color basically means hot, like there's a lot of electrons there. This bottom side is more blue, which is kind of like a cool color, which means not so many electrons are found there. So this is sometimes what is referred to as like a electron density sort of map, and that's what the sort of those colors sort of mean. Here's our NH3, and again, if you draw NH3, you could apply the same approach we just did. Again, I have dots. I got everybody the same. I have a polar molecule. And not drawn here, but there are some non-bonding electrons happening here. So in this case, everybody's pushing in towards the nitrogen, and the nitrogen and those non-bonding electrons are actually pushing out a little bit with them. And you can kind of imagine kind of net movement happening in this direction, hence where we see our dipole moment happening, nitrogen being more negative, the hydrogen side here being more positive in this particular case. Again, even though it has technically 4 electron pairs, it is that lack of that fourth bond, and it gives it a little bit more movement that we have, this sort of net movement that would happen. And then, for example, if we went out to one more hydrogen on there, this guy technically, based on geometry, would be nonpolar, because just like we see to the left, we got all 3 of these guys heading in. But the difference is we have this guy heading in as well. So if you kind of converted this into ammonium, this guy would be pushing back down on this guy. And now we got all 4 guys symmetrically spaced out, pushing in on the nitrogen, and the nitrogen pretty much won't go anywhere if you want to think about that. And again, that's why in something like ammonium, the NH4 plus, based on geometry, would be nonpolar. But something like ammonia, where we lose that last bond and replace it with the non-bonding electrons, becomes something that is polar. Question on that there. What does molecular polarity affect? Well, it does affect how things are attracted to each other. And basically, things are attracted to each other by a very simple concept. Most molecules are attracted to each other by the very simple positive negative attraction, that electrostatic attraction. So why would sort of these things affect things like solubility? Well, if you take something like water, which is negative here and positive here, And maybe you take something like sodium chloride and you put it in water where it makes a sodium ion and a chloride ion. This positive sodium ion would be attracted to the oxygen there. And that's how things dissolve, actually. A bunch of water molecules and their oxygens are essentially attracted to the positive ion there. And the negative ion, same thing happens though, but it's actually the positive side of water, which would be the hydrogens that are attracted. And that's how something dissolves, because they basically go around each of those ions and it prevents those ions from coming back together and making a solid, and then it dissolves. Something like oil and water, water again being polar, negative and positive over here on the hydrogens. Oil is pretty much nothing but a really long chain. I'll just draw 4 of them, but a lot longer than this chain of carbons attached to carbons, which is nonpolar, and carbons attached to hydrogens, which is nonpolar, which means this guy, for the most part, has no charge. He's nonpolar. Water is polar. And what water is looking to do is find something with a charge so it can interact. And since this oil doesn't have any type of charge because it's sharing its electrons equally, you can see here oil and water do not mix. And it's because of that, they have no long range, way, I guess is a better way of saying that, to interact with each other because of that. This is what is known as intermolecular forces. And essentially, again, they really don't have that long range way to interact with each other. And usually what happens is what we see there, the oil will essentially separate out. Any questions on that there? Okay. That's soap. Here's just a few examples here. We'll just kind of finish it up since we have, I think, one more slide or two to go, just to kind of finish. If we look at these two things, again, we want to kind of look at, a couple things. Do they have polar bonds, right? And so, for example, if we look between nitrogen and oxygen, the difference in electronegativity between nitrogen and oxygen, nitrogen is 3, oxygen is 3.5. So the difference there is going to be 0.5, which means it is polar, and we would have a polar bond heading in that direction. Between nitrogen and chlorine, though, when we do the difference in electronegativity, the difference is actually 0. It's 3 minus 3. So the thing we want to look at here, though, is the geometry. This has 3 electron pairs and 2 bonds. That, again, is going to be our angular shape. So now when we kind of draw the geometry part in, and we got that guy pulling this way, it's essentially like somebody going down to the oxygen side and just pulling, right? You could kind of imagine the whole thing kind of moving with it, and it would be a polar molecule. And by the way, you could probably do the same thing we did before. I see dots, even though they're not the same on the outside, as you can see here, probably a good chance that they're going to be a polar molecule anyways. If I look over here between sulfur and oxygen, sulfur is 2.5, oxygen is 3.5. Difference in electronegativity is 1, which means it is a polar bond heading towards the oxygens in each of these cases. Geometry here is 3 electron pairs, 3 bonds. That is trigonal planar. And again, at this point, you don't really even need any of that. You could just simply look at it and go, no dots, everything on the outside the same. You should hopefully say it with me. This should be nonpolar molecule here. And this would be a nonpolar molecule. Again, not really drawn geometry-wise, but basically trigonal planar means like a triangle. And you basically got at the corner of each of those triangles, everybody kind of pulling equally. A question sometimes people ask is, does the double bond affect it? And an answer is no, because if you remember, we treat a double bond or a triple bond as if they were one bond, right? So even though it's a double bond or triple bond involved, it's effectively moving like one electron pair and kind of one bond, so it will have no effect on this type of thing. So that guy would definitely be nonpolar. Any questions on that there? That will wrap up this chapter.